All right, everybody, welcome to the Engineering Dynamics crash course. And this course is modeled off of the Virginia Tech 2304 curriculum, but of course, this can be used for any engineering dynamics course because I covered all of the major topics in dynamics throughout these 8 hours of lectures. Okay, the primary goal of this course is for me to help you understand the 4 parts of dynamics, which I'll go over shortly what those 4 parts are, and then most importantly, understand how systems work. Okay, engineering dynamics is sort of one of the last courses that us engineers use in order to really understand how systems work as a whole. Okay, a lot of us go into engineering, I know myself included, a lot of us go into engineering to understand things that we wanted to learn or build as a kid. I remember seeing like cars, seeing airplanes or trains or whatever, and looking at them and wondering like, how do these things work? How do all this stuff that comes together and makes this happen, it's all magic, okay? So now we are gonna show that it is not all magic indeed, right? So kind of the progression of courses that lead you up to engineering dynamics are first, like our physics course, of course, which helps us understand the laws of physics. Following that is statics, which helps you understand systems that don't move, okay? So in dynamics, we are actually going to revisit some statics problems, except this time there's going to be some motion involved, hence the name dynamics, okay? And after that, deforms sort of gets run parallel with dynamics. I know many universities teach deform and dynamics in parallel, so you take them at the same time. Deforms will talk about more specifically the materials, of course, deflection, statically indeterminate problems. You can combine that knowledge with the knowledge from this dynamics course to help you get a complete picture of any system that you are trying to analyze. All right, so let's get right down to it. So the notes that I have written here are, I'll be following this set of notes throughout the entire course. I wrote the notes fairly large and I tried to leave some space on each page so you can jot down notes if you prefer. But I designed the notes in the course so that you really only have to listen and you don't really have to write down a whole lot. All right, so let's get started. So the goal of dynamics is first to understand how systems behave, right? So that's the entire goal. We want to look at something and be like, well, if we move this much, how much does this move? Or if we apply a force of this to this part of the system, then what will happen here, okay? So that is kind of the overarching goal of dynamics. The next thing is we're going to be learning kinematics versus kinetics, okay? So kinematics is the way it moves, okay? So studying just the equations of motion, right? So movement only, okay? Movement only, all right? And kinetics is the forces or moments behind that movement, okay? So if you are trying to study kinetics, you're only concerned with how the particle moves. You're not concerned with how much it weighs or anything like that, okay? Kinetics is talking about the forces that produce this sort of movement, okay? The other 2 categories that we're going to be talking about is going to be single particle, okay? So, single particle motion, obviously it's a dot, right? With some arrows sticking in and out of it to represent our forces, or perhaps just some equations that represent the motion or kinematics, okay? And next one is going to be rigid body systems. Okay, so in Physics 1, which is sort of the class that immediately precedes this class, you mostly spent all your time talking about single particles, right? You didn't really spend time talking about having a car with 2 wheels in the ground. You just assumed that the car was a point particle and you did your analysis that way. The only time when you talked about rigid body systems in Physics 1 should have been when you talked about the mass moment of inertia, when pulleys all of a sudden had mass and they weren't massless. Okay, that's pretty much the only time that you talk about rigid body systems in Physics 1, but in this class, we're gonna be going into a lot more detail, right, with both kinetics and kinematics for both. So as you can see here, there are 4 topics, but these aren't like the 4 topics that we're going to talk about in the class, they're actually going to be a combination of these. Okay, so essentially what we're going to do in sort of like section 1 of the course is going to be kinematics of a single particle. Okay, that's going to be part 1 of the course. Okay, and then part 2 of the course is going to be, I think it's kinematics of rigid body systems. Okay, so we're just going to talk about just the motion of rigid body systems, and then we're going to be talking about kinetics of single particles, okay, which obviously means the forces that make this thing go places, okay, or do things. And then of course, lastly, you guessed it, we're going to be doing kinetics of rigid body systems, which kind of takes everything that we learn in this class and bring it all into a single cohesive bunch of formulas, if you will. Okay, so the basis of this class, of course, is that we say the sum of the forces is not equal to 0, okay? All right, and that's the course. All right, have a good day, guys. No, I'm just kidding. All right, so the idea is, of course, from statics, we had systems, right? And most of the systems in statics that we learned were systems that do have the capability of moving, right? But we assume equilibrium, okay? But now we're going to make this assumption, right? So we cannot assume that things are gonna always equal 0 because the class is called dynamics, right? Okay, so how do we tackle problems? All right, now this is the Scott method of tackling problems. I didn't patent this, but this is the method that I use whenever I tackle any sort of dynamics problem. It doesn't even have to be dynamics. It can just be an engineering problem in general, okay? Remember, guys, all right? I'm not here to test you. I'm not here to give you a quiz, okay? What I'm here to do is to help you understand engineering, right? To help you think like an engineer, all right? So when I tackle any engineering problem, even outside of dynamics, it could be mechanical design, vibrations, just designing something for my car, designing something for the company I work for, whatever, okay? These are the kind of steps that I'm going to take in order to understand what's going on, all right? Of course, I've catered that a little bit towards this class, all right? So the first thing you're gonna ask yourself is, what's going on? Okay, for those of you who have either had me as a tutor before or have taken any one of the other crash courses that I offer, well, the what's going on question shows up every single time, all right? So if you know me already, then you know that I'm gonna ask you this question every single time we come up with a problem. And the reason why is because knowing what's going on in a problem is going to help you understand what your answer should be, okay? It's gonna help you understand, well, okay, well, if I drop this or if I move this, then what are the consequences, right? What are the mechanical consequences to changing my system, okay? Before you do any of that stuff, you need to understand how the system works just by looking at it. You know, you don't need to say, oh, this is loaded in double shear, this has a stress of this. No, I just want you to, in your head, be able to imagine like the thing moving by, like, right, actuating, okay? So it's sort of like a bicycle, right? If you guys can imagine what a bicycle looks like. If you pedal the pedals, okay, your rear wheel spins. Why does it spin? Because there's a chain connecting them, okay? That's really all that you need to know when you're riding a bicycle, right? You're like, okay, well, that kind of makes sense, right? So the next step is to draw a picture. Okay? And the reason why I tell folks to draw a picture, especially in this class, is because the systems tend to get a little bit more complicated than they were in statics or physics 1. So while you were able to get away with using the picture provided in those classes, in this class, it's a lot more beneficial to draw yourself a separate picture, right? Simplify it down. Don't leave in all the details, right? I don't need the detail of like each grain of wood fiber that runs through my drawing. I need a simple stick figure with a bunch of forces sticking out of it to represent my system, okay? So the key to this part is this part, okay? If you draw a bunch of stick figures, you know, if anyone comes by and looks at it, they're not really gonna know what you're talking about, but if you understand what's going on in the system, you can look at this very simple free body diagram and say, oh, okay, well, I know how this is gonna work. And the simpler the diagram is, the easier it is to analyze, okay? Now, when I say simple, I don't mean lacking detail, okay? You need to include all the details that are necessary in the problem, but don't include too many details where it clutters up your thought when you're looking at it, okay? The next step is to identify what you know and what you don't know. All right, so knowns and unknowns. Okay, so we need to identify the things that are given to us in the problem, and that could be something as simple as just circling the numbers that are given to you in every problem, okay, and circling some key information such as like the word clockwise or the word left or the word after 5 seconds, okay, so circling all that information and identifying, of course, your unknowns. Okay, now your unknowns can be, what is the question asking you for, right? It could definitely be, you know, at the end of the question it says, oh, okay, so how many seconds does it take for blah, 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 then you know, oh, I'm looking for time, right? I'm looking for some sort of duration, okay? But that might not be the only thing that you're looking for in the problem, so it's your job to look at all your knowns and your unknowns and say, okay, well, what other variables could potentially link me from my knowns to my unknowns, okay? So that's just going to be a little bit of intuition. Of course, you guys probably don't know exactly how to do that now, but throughout the crash course, we will be learning that process, okay? Number 4 is gather relevant equations to relate your free body diagram to what's going on, okay? So we drew the free body diagram, right? So relate, essentially, number 2 and number 1. Okay, so we drew the free body diagram, we know what's going on, okay, and we have a bunch of variables that are, you know, labeling our free body diagram and a bunch of parameters that we have written on the side, okay? So the question is, how is the free body diagram and how are the variables related to what's going on? Okay, now this is like the key step in learning dynamics or understanding any system, okay? Now, and the reason why is because this sort of helps us kind of put together a cohesive picture. We say, okay, well, if the time is this, and then maybe if the time is 3 seconds later, then what happens to the end of my rod that goes up and down, right? Oh, well, because I know what's going on, then I know that it's gonna be up here, okay? Well, if I know it's gonna be up here, is it going in a curved motion or a straight motion? And from that, you can generate an equation that relates your unknowns, your knowns, and your picture, okay? So at this point, number 4 is the point where you will gather the relevant equations, all right? So, and this is kind of like, in Physics 1, okay, in many of the physics courses, of course, I don't know how it is in other universities, but in many physics courses, this step right here with the equations, okay, is it just a matter of scanning your formula sheet for a bunch of equations that, right, that kind of relate everything together, and that's how everyone got through Physics 1, by just having a super complicated formula sheet and just looking for the equation. Well, I started to break it to you, that's not the way dynamics is gonna work. Okay, you can't just have a super complicated formula sheet and parse through it to get what you need to get, okay? So you need to be able to logically relate these first things together in order to understand which equation that you need to use, okay? All right, and of course, last one is formulate a plan of execution, right? So odds are you're not gonna have a single equation, because that would be way too easy, okay? And like I said, that's the reason why you can't just parse your formula sheet to find a single equation. You're gonna need multiple equations. Usually it's gonna be 2, 3. Towards the end of the course, we will have 6 equations and 6 unknowns, okay? Which is not something that you're unfamiliar with in statics in 3 dimensions. Remember, we had 6 equations, 6 unknowns. These equations happen to be all different from each other, so the 6 equations will not necessarily be related. But anyway, so we're gonna have a plan, okay? So we're gonna take the equations that we found and formulate a plan, right? Oh, I'm gonna use this equation to relate these two together, and then once I get this, I'm going to use a different equation to relate this, okay? So don't try to tackle any problem unless you have a plan, okay? Because otherwise, you could potentially be running in circles, all right? And you don't wanna do that. All right, so the idea of This whole thing, okay, of course, stems on the fact that you know what's going on in the problem, okay? And a clever way that I always use to teach my students is to, when you ask yourself what's going on, you need to say, okay, well, if I poke the system this way, what does it do, right? If I quote unquote perturb the system, right? If I apply a perturbation force to the system, I poke it, what happens, okay? And or what happens if I remove a part of the system, right? If I remove the kickstand from my bike and I let it go, what happens, right? So these, of course, relatively obvious, but there are some systems that we're going to see that are not so obvious. And when you remove parts, when you add parts, okay, and you guys are wondering, well, you know, the system that I'm analyzing is not going to have extra parts or remove parts, you know. Why should I care about that? Well, if it gives you a more holistic view of the system, then just try modifying it in your head, all right? Move it with your hands, right? Push it, pull it, hit it, okay? Add parts, remove parts. That's gonna help you understand what's going on in the system, okay? All right, so before we do that, or before we move on, when we draw a picture, we are gonna have to draw a bunch of forces acting on it, right? So we're going to draw the free body diagram. First, we need to understand what kind of forces that we are going to be using in this class, okay? And of course, there are many types of forces, but the types of forces that we are going to be using in this class are going to be limited to the following for the most part. Of course, you may see some weird other force, but in general, these are the forces that you're going to see most commonly. Of course, there's going to be a normal force, okay, which is the force of a surface pushing back on an applied force. So for example, if I'm pushing on the board, the board is pushing a normal force back towards me. Okay, there's going to be gravity, right? One of the only forces that does not require physical touch. Of course, if I throw something in the air, gravity acts on it even though nothing is technically touching it. It's going to be a frictional force, which acts only opposite in the direction of motion or opposite of the direction that the object wants to move, because the object doesn't necessarily have to move in order for friction to be a thing. All right. Tension, which can only go in one direction, right? Because you can't push something with a string, you can only pull it. Spring force. Okay, spring force, of course, we'll only see a spring force in one section of this course, okay, when we talk about energy, which is something that we've already talked about in physics. Okay, but springs have just a simple equation that go along with it, as you guys already know, Hooke's law. And the last one, of course, is our point force, which is sort of just anything that is touching your object, like if I'm pushing it or if I'm grabbing it, right? Those are point forces and can be treated, of course, like a regular force. Okay, so these are all the kind of forces that we will see in this class, all right? So, of course, forces are not going to be discussed until we talk about kinetics, right? In the first part of this course, we are going to be talking about kinematics of particles. So let's go ahead and discuss that. So like I mentioned, kinematics is only the study of motion. I do not care about the mass of the particle, okay? I only care about how it moves, or the acceleration, okay? So therefore, I'm not really concerned with the forces or mass, okay? The first type of kinematics that we're going to talk about is rectilinear motion, okay, which is only the x-y axis, okay? Now, there's just some notation that I would like to go over. Of course, this is all written in your notes, but our S is called the position, okay? Of course, the derivative of the position ds dt is equal to the velocity, okay, as you guys already know from calculus. And then, of course, taking another derivative, the second derivative of our position, as you already know, is going to be our acceleration, or the first derivative of velocity. So, okay, great. So from these equations, okay, we can come up with some differential equations. Okay, and the differential equations, okay, is going to be relatively simple. You don't actually need to know differential equations, like the differential equations course, in order to solve these. This just turns out to be, if I multiply dt to the other side, I get ds equals v times dt. And if I do the same thing to here, I get dv equals a dt. Okay, and suppose I want to get rid of dt, take the time factor out of both of these. I solve them both for dt, I set them equal to each other, I combine them together, and then I get the following. A times ds equals v times dv. Okay, now these formulas are just the three, sort of like the three kinematic equations that you were given in Physics 1, except the calculus version of them. Okay, so this one is the s equals, right? So if you take the antiderivative, right, you'll get s equals v times t plus s naught, and then of course here you'll get the v equals a times t plus v naught, and then for here you'll get that other weird one with the v squared, all that funny jazz, right? So there's that, right, for these. Okay, we'll be using these, of course, throughout this entire lecture, but if we consider our acceleration to be constant, because the beauty about these is that a does not have to be constant. Recall from Physics 1 that the acceleration value that we used had to be constant, right? We said a was equal to 2, a is equal to 9.81, okay? But for these, our acceleration does not have to be constant, which is why we are covering this material again in dynamics, because it is a little bit different, okay? Now, if our acceleration is constant, okay, which it will tell you in the problem if it is constant, okay? If it'll say either no acceleration or the term constant velocity, which of course means no acceleration, right? So if our a is constant, right, then we get the following equations. V equals v naught plus at. In addition to that, we get s equals s0 plus v0 times t plus 1/2 a t squared. And then lastly, we get vf squared equals vi squared plus 2a delta s. Okay? Or we can say, keep it consistent with the notes. Okay, v squared equals v0 squared plus 2a times delta s. Okay, like I said, these are only for constant acceleration. Okay, constant acceleration. So we have here, notice that all of these formulas can be a little bit overwhelming, right? But at the end of the day, what we can see is that there are only 4 unknowns total. Right? There's only 4 variables in all of these equations, right? What are they? Right? Time, position, velocity, acceleration, right? Every single one of these equations has some combination of these, okay? So when you're looking at a problem, usually it's going to be asking you for one of these things, and it's going to give you some other stuff, right? So it could potentially give you, a problem, I'll take out another different color marker, okay? So if a problem says, we're asking about the acceleration and you're given these two, okay? You're like, okay, well, I don't care about time, right? So which one of these equations doesn't have time in it? Oh, this one or this one, okay? Question is, do I expect my acceleration to be constant? In this case, because it's asking you for the acceleration, it's going to be constant most of the time. So therefore, we use this equation, right? So let's try again. I'm making these up off the top of my head, right? So let's see. Asking you for velocity, and it gives you time and position, okay? So which one of these equations does not have the acceleration in it, okay? Or in other words, well, actually, technically, this combination actually will never be given to you, because if it's asking you for the velocity, it has to also give you the acceleration, right? But if it does give you the acceleration, suppose it does, either it'll tell you what the acceleration is, or it'll tell you that the acceleration is equal to 0, okay? In which case you'll know, right? But either way, okay, you're gonna pick this one or this one, right? Okay, because if it has time in it, you're stuck picking one of these four, right? And if it has position in it, you're stuck picking one of these two anyways, right? So then you say, okay, well, is my acceleration going to be constant? In this particular case, yes, it will be because of reasons, right, that you don't need to know. But you say, okay, well, it's going to be this one now. Okay, so at the end of the day, for these types of problems, it's excellent practice to be able to identify your unknowns, be able to identify what you're looking for, and then be able to sort of quote unquote pick one of these equations. Okay, so so like I said, from the first kind of 4 steps that we talked about on the first page of notes, this is a great practice to say, this is what our situation is, this is what's given to us, and this is what we need to find. Okay, it's a good introduction, but unfortunately, all the equations won't be laid out as beautifully as this as we move on in the course. Okay, but with that being said, we are going to do an example. Okay, so it says if a particle moves with some sort of motion a equals 2 times the square root of v, find the velocity when our position is equal to 2. Okay, so in this entire problem, it's asking us for the velocity at a certain position. Okay, so in physics 1, you have not seen a problem like this, which is why I picked this problem. Okay, usually velocity is a function of time, right? We say v of t. But in fact, velocity can be a function of position, okay? And when we don't care about time, which kinematic equation do we pick? Well, we're gonna pick, if you guys recall from before, it was the one all the way over here, okay? Now, is our acceleration constant? No, right? Our acceleration is a function of the velocity, and our velocity is a function of the position. So therefore, we're going to pick, right, a ds equals v dv. Okay, now all we have to do is just plug and shove. So our a is equal to 2 times v to the 1/2. We're just going to take that and just throw it right here. And when we do that, we find 2v to the 1/2 ds equals v dv. Okay, now this is where you need to know about 1% of differential equations in order to solve this problem, okay, because this method, I believe it is the chapter 2 some part of chapter 2 in the differential equations textbook, but this method is called separation of variables. It is very straightforward. Your goal is to separate the variables. You want to put one variable on one side and the other variable on the other side. In this case, we want to put s on the left and our v's on the right. So in order to get this v over to the other side, in order to solve our differential equation, I will simply just divide by v to the 1/2 on both sides, and we will get the following. 2 ds equals v to the 1/2 times dv, right? So now our variables are happily separated, all right? And now what we are going to do is solve, right? When we solve, all right, we are going to try to get rid of our ds and dv, right? And the opposite of the d is the integral, okay? So we're gonna place the integral sign here, and the question is, what are the bounds going to be? Okay, what are the bounds going to be? Now this is a little bit interesting, all right, because normally you would put numbers inside the bounds. Okay, normally you put numbers inside the bounds, but not in this case. In this case, we can actually put variables inside the bounds that represent our initial conditions, all right? In order to do that, we're gonna say, well, what is our initial position? Okay, our initial position, it doesn't necessarily tell us in the problem. I didn't necessarily tell you in the problem, right? But we're going to assume it starts at the origin, right? Because otherwise, if it doesn't start at the origin, it would tell you for sure where it starts, okay? But it doesn't tell you, so you're gonna assume that it starts at the origin, so my initial position is going to be 0, right? What is the final position that I care about? x equals 2, right? It should have put s equals 2, but you know, same thing. So s equals 2, okay? Our initial velocity, 0, right? I said if it should tell you that it starts from rest, okay? In an actual problem, it'll say particle starts at rest and then has some acceleration equal to 2v to the 1/2 or whatever, so 0. What is the final velocity? I don't know. I don't know what the final velocity is, right? So therefore, I'm just going to put v f or v. So technically, okay, if I put a v here, that's illegal, okay, because I already have v's right here, okay? So as you guys recall from Calc 1, you technically have to use a dummy variable and do all this stuff, right? So to simplify that, you can, of course, use VF. If you do put a V here, that's the same as these V's. I don't think you're gonna lose any points, but it's just any math professor would probably lose their shit if they saw you do that. So you can put a VF there if you like, but personally, I don't most of the time. So after that, you solve. Now let's look, because how many unknowns do we have? After we solve these integrals, the only unknown that we're gonna have is VF. Okay, VF is gonna be the only unknown. If I solve it, hopefully, I'm going to come out and get a number. All right, so let's go ahead and solve it out. We find that we get 2s integrated from 0 to 2 equals the antiderivative of v to the 1/2 is going to be 2/3 v to the 3/2 integrated from 0 to VF. And then we get, see, this turns out to be 4. So 4 equals 2/3 times VF to the 3/2. Okay, so as we expected, we have a single unknown here, which is going to be VF. Of course, solving for that gives us, so we get VF to the 3/2 equals, so you do the thingy times 6, okay, and then VF is equal to 6 to the 2/3, which I found to be approximately 3.3, so technically meters per second. All right, so the question is, what does this represent? This is the velocity when my particle is at position x equals 2. Okay, so a fairly straightforward example of rectilinear motion, but that is kind of the main topic, all right, for rectilinear motion. The other main topic that I would like to cover is projectile motion, right? So this is sort of like general motion, right? General motion in space. This thing is just zooming along in one, this is, by the way, this is one dimension, right? This is a single dimension, so like a number line, right? This particle acceleration is described by a single thing, right? When you get into 2 dimensions, you could use vectors, okay? Or you could use parametric equations, which is what we're going to talk about right now. So the first thing I want to talk about is a little bit about notation, kind of just reviewing the notation from statics, I think deformed maybe, but vectors are something that you guys have covered in multivariable calculus, you've covered it in statics, you've covered it in physics, so I'm not gonna beat it over your head again, okay? But just a note about the way we notate things here in this class. Our velocity is just equal to Vx comma Vy, which is equal to Vx I hat plus Vy j hat. Of course, the I hat direction is corresponding to the x direction. The j hat direction is corresponding to the y hat, or the y direction. Okay, and of course, if we like, we can put a z component in here as well. Okay, and in this class, we use a dot to represent the derivative, right? So, for example, our s dot is equal to ds dt. Okay, just a note. So we don't actually use the prime notation to represent derivatives in this class. In general, in calculus, the dot means derivative with respect to time, okay? The derivative with respect to time. So if you use prime, usually prime is a spatial derivative and dot is a time derivative, okay? Most textbooks follow that convention, all right? Now, the thing that's different in this class is that we don't use prime for spatial derivatives because we hardly use spatial derivatives. We actually just did on the previous one where we had the ds, right? But anyways, the prime notation is generally used for after, okay? So for example, if I say like, well, you guys will see later on, but if I say v prime, it means the velocity after something happens, okay? So just to note that v prime does not mean the acceleration in this class like it did in Calc 1. All right, just a quick note. So with that being said, the dot notation and the derivative stuff can get a little bit confusing when we talk about vectors, okay? So I just want to do a little bit of a note with this, okay? So v, okay, the vector v is, of course, you guys know dr dt, right? Or ds dt, right? So, but ds being like ds with an arrow on top, okay? So this is equal to r dot, okay? Because the ddt notation here just gets thrown into the dot here. As you guys can see, this is a lot simpler to write, okay? But we need to note that this is not the same, okay? It's not the same as writing this, okay? So like, these are not the same quantities, right? Like if I take the magnitude of this, I shouldn't get this, okay? So just be a little bit careful. You'll know, there's probably a few instances in this class where we'll go over, where we'll encounter something like this, but just be careful on your notation as you move through the course, okay? Now, by the way, this is the magnitude sign, right? So the magnitude of the velocity, right, is equal to just the standard non-vector form of my derivative of position with respect to time, okay? So we'll probably see maybe one or two examples of this throughout the course, but as you go through your practice problems and homework problems, just remember, ask yourself, are you supposed to be using vector notation here, or are you supposed to be using a linear notation, okay? So hopefully we'll see that throughout this course, but we may or may not. Okay. So consider a car traversing a turn, okay? Consider a car traversing a turn. It has some sort of R1 and it has an R2, and now the R1 and R2 are not necessarily the same, just I'll even changed it, right? And it kind of traverses a turn like this, all right? And I know that the velocity at any given point is going to be a velocity at any given point. Why did I? So this should actually be R1. This should be R2, right? So because it's going from here to here, right? So it makes sense that this is going to be v1. Okay. So we know that our acceleration, right? Our acceleration is going to be equal to the change in velocity over the change in time, okay? So it will be v2 minus v1 divided by t2 minus t1. Notice how, of course, only the top is a vector. The bottom, you can't divide a vector by another vector, all right? So that is sort of a visualization, right? So you take this vector and then minus this vector and then divide it by the amount of time. That will get you your acceleration vector, okay? You're probably not going to be asked to actually draw vectors like head to tail in this class. I mean, maybe for like a 2-point question on the exam, it might give you that, but that kind of thing should have been tested in physics, okay? So we end up with the following relationships when we do vector relations. So we'll get r of t equals x of t, y of t, and then v of t equals x dot of t, y dot of t, and then our acceleration equation relationship becomes x double dot of t and y double dot of t. Okay, so we can, of course, take the magnitude of any of these by taking the square root of the first component squared plus the second component squared. If you guys remember that from statics, probably from deforms and a bunch of other classes. Okay, just recall that for example, we can use the v of t, right? Just so we can practice the notation a little bit, kind of review before we move on to some more interesting stuff. Okay, this is what we call parameterization. Okay, and the word parameterization is a word that you are also going to see in multivariable calculus. It turns out that it is a very fancy terminology for saying, okay, we're gonna pick a different set of independent variables. Okay, so my position is dependent on time and time, right? So my x coordinate is dependent on time, my y coordinate is dependent on time. So that means that the system or the equation is parameterized with respect to time. Okay, that's all that really means. All right, so don't get too freaked out when you hear the word parameterize. Okay, so we'll see it in multivariable calculus, and we'll see it in this class. All right, and the first thing that we're going to do in order to practice our parameterization is going to be projectile motion. All right, so this is something that you all have already seen in Physics 1, but I think the way they tackle it in this class is a little bit more challenging because it asks you for a different set of unknowns sometimes, and I'll try to give you guys all the equations that you're going to need to know in order to tackle those problems. Okay, so you guys have seen this picture before. It's just a simple projectile motion problem, right? Now, in order to find the x and y positions, we have the following. Of course, in the x direction, there's no force acting on this thing, so the acceleration is going to be 0, and we only care about the x component of the force, right? X component of the velocity, excuse me, right? Which is going to be v naught times cosine of theta multiplied by t. Okay, that is going to be my x position. My y position is going to be just a little bit more complicated because it is subject to the acceleration due to gravity, and I care about the initial y position, which you may or may not want to put in there. Okay, so it's the initial y position plus v naught times the sine of theta times t. Okay, now this is just the linear component, right? So check that. This is just a linear component, and then minus 1/2 gt squared. This equation is something that you've already seen before. Okay, now suppose that you are interested in simply like range or like other things like that that don't necessarily care about time, right? If you throw a ball, right, if you're like throwing shot put or something like that, right, you don't really care about how long the shot put stays in the air, you really just care about how far you throw it, right? So these two equations are great, but there are some ways to manipulate them to get some more information out of them, okay? So one way is to find the time of flight, okay? So the time of flight is just how long it takes to go from here to here, and the time of flight is going to be based off of this equation, right? Because this equation tells us where we start and where we end, okay? Because this y of t is a parabola, right? That just gives you that 0 intercept, the roots here, okay? So setting y of t equal to 0 gives you time of flight, so we call it tf or t flight sometimes, all right? And then the magic happens when you talk about the range, x range equals plugging in a time of flight for my for this equation right here. Okay, so it's gonna be x range equals x of this, so like plugging in time of flight into this part. Okay, but suppose that we don't want t, right? So let's suppose I don't care about time of flight, like I said before. I only care about the range, okay? Or I only care about where something is with respect to x, right? So the height with respect to x. Well, what we can do is we can solve this for t and plug it into here, which we're gonna do right now. Let's solve our x for t, so we're gonna get t equals x divided by v0 cosine of theta. We're gonna plug that into my y of t equation and get y of t equals y0 plus v0 sine theta multiplied by this thingy, which is gonna be x divided by v0 cosine theta minus 1/2 g times x over v0 cosine theta squared. Whew. Okay, now, of course, we could simplify it. We see some stuff cancels out. We get this. Sine over cosine becomes tangent. So the overall equation that we get for our trajectory is going to be y of x. Okay, so no more t anymore. Okay, this y becomes an x. Y of x equals y0 plus tangent of theta times x minus 1/2 g times. Of course, you could distribute this out. You could do whatever you want to it, but I sometimes like to keep it the same. X over v0 cosine theta squared. What kind of equation is this? It looks a little bit scary, but theta is usually known. So x is your unknown. It's just a parabola. Okay, as you'd expect, a parabola, right? Because it's just x squared, and then it's x, and then it's a constant. Okay. Now, if it asks you for theta, a launch angle, okay, you can use your calculator to figure that out, right? Just solving like the intersection of two graphs, or if you have an Inspire, use the solve function. Now, if you solve, usually you're going to get two values of theta, okay? When you solve for a theta in order to create a projection, you're gonna get two values of theta. Now, if it's an impossible situation, for example, like no matter like what angle you launch, you're never gonna get to that range, then it'll tell you no solution, okay? So that is sort of a way to gauge and to understand what's going on in your problem, because if it says, hey, we're gonna launch this thing at 5 meters per second, which is not that fast, right? That's about the speed of like a, I don't know, like a middle school track runner, okay? 5 meters per second. What is the angle required for launch in order to reach 100 meters or like 200 meters away? Okay, and then that makes you scratch your head and say, well, I don't think the angle really matters because it's just gonna go, right? It's not gonna actually go that far, okay? So if you get theta equals not a number or no solution, then you know that you don't have enough velocity to meet that criteria, okay? But in general, if you launch something, okay, you're gonna have a low value for theta, and you're also going to have a high value for theta too, okay? So as you guys know, you can either throw something like kind of line drive like this, or you can throw it like super high in the air and still reach your goal. Of course, in most sports, you really care about throwing it in a more direct way, less time in the air, and so on and so forth, okay? So that is one of the uses for our vector equations, right? We can of course write our vector, our v of t, to be equal to x of t, y of t, right? Parameterize. But more importantly in this class, you probably will be using this equation to some extent as well, okay? So those are all the equations that you're gonna need to know for this particular section of rectilinear motion, right? It is the 6 equations we talked about on page 2 with the 3 differential ones, and then the 3 normal kinematic equations that you had in physics, and then it's these equations that you will need to know for your projectile motion, okay? And that is it for this lecture. In the next lecture, we are going to talk about the other types of two-dimensional coordinate systems. The first one being the normal and tangent coordinate system. The next one being our r theta coordinate system, which for those of you guys who have taken multi, you'll be a little bit familiar with. And then the last thing I want to talk about in the next lecture is going to be relative and constrained motion, which are actually pretty interesting topic. It's a little mind-boggling to get your head around, so I would like to spend a little bit more time on that. Okay, and with that, I will see you guys next time.